just a couple of words of thanks before we get started with the presentations. First of all, to our hosts here, the Commonwealth Bank, especially Perry Stevenson and the talent acquisition partners, Manish Mirani and Rebecca Wallace. So they kindly provide the venue and food and drink. So thank you guys. Anyone in stop Perry? Thank you guys very much. And if you want to talk, if you want to find out more about maybe working at CVA, these are probably exactly the people to talk to in the break. Then there's Greg Pearl from N-World, who brought us on sign. So if you're unsure who it is, go to the sign. He's sponsoring our videoing drive back there. Thank you very much. These presentations will go up on our YouTube channel, Data Science Sydney, as well, so you can look at past presentations from the last few years on there as well. There are a few real gems on there. And last but not least, Prescient and Eugene Dubozowski, our second speaker, also one of our main sponsors. Without his support and with all the other sponsor support, this meetup wouldn't be possible. So guys, thank you very much. And a quick structure of today. So we'll have two presentations. First one about 25-ish minutes, and then 5 minutes time for questions. We'll have a quick break for refreshments after that one. And then the second talk, and Eugene just told me he'll talk straight through and take no questions at all. That's the plan. So long talk, lots of content, very much looking forward to that. Yeah, and then we have till 8:30 to mingle here and network really seriously. And after that, please remember your badges as you exit the building. That's all from me. You're welcome. And with that, I would like to introduce our first speaker, Sachin Abeywardana. Close enough. Sorry, totally butchered that one. We'll talk about generative adversarial networks, and I'm really glad we have Sachin here today. He's probably one of the leading experts in deep learning here in Sydney. He's author of Deep School IO, which is an open source and free framework for teaching deep learning to software engineers, which has currently more than 1,000 stars on GitHub. Sachin graduated from the University of Sydney. First, he did a first-class honours in mechatronics engineering, and then he did a PhD in machine learning. And now, well, the stage is all yours. Great you're here today. Generative Adversarial Networks. Sachin.
Thanks, everyone. So, what I'm going to do, first of all, is just go through the project that covers this whole thing before I go into GANs in itself. So deepschool.io, it's a bit of a side project that's pretty much somewhat gone viral in the sense that it's a teaching framework for deep learning. But one thing that I do here is I tend to skip most of the maths and try as best as I can to make it easier for a lot of people. And if you're very new to deep learning, one thing you can do is if you go to deepschool.io, you'll get redirected to the GitHub page. And if you go down somewhere here, this thing called Launch Binder, which launches a free instance where you can play around with all these all the notebooks that are in here already. Right, so it is in Python, so you do need some Python background before you get started on any of these things. But yeah, and and I also maintain a YouTube channel which I go through most of the tutorials in here. Right, so now I must admit that generative adversarial networks, it is one of the more advanced topics, so that's why it's right at the end down there. Right, so but at the same time, hopefully you will get something out of what I'm about to go through today. Yeah, so, and we do have a meetup, which you will find all the details in here as well, where I actually help you out going through these examples. Okay, so, all right, so let's skip right to the beginning. So GANs, it was actually a 2013 paper by Ian Goodfellow, and even though it's only been 3 years since.
Could you zoom a little?
Oh, right. I'm not actually going through the text
okay.
in here. Yeah, so even though it's only been 3 years, there's actually been an explosion in GANs, right? So GANs actually, in my view, actually created a new domain within deep learning in itself. So what's interesting to me is that deep learning people usually tend to do either regression problems, classification problems, sometimes unsupervised problems, but the whole idea of generating data, which is mainly a domain of, I guess, the probabilistic people, so the Bayesian people, so it's mostly been untouched. So GANs is a very new way of looking at generating data, but at the same time, it's quite intuitive as well, right? So the idea is it's quite simple. Yeah, so I'll just go through. So the general idea is, so suppose I have this a completely random data set, right? And the idea is that I need to learn a function that will transform that data set into a different data set. Okay, so in this case, if you think about the inverse CDF of a normal, so this thing over here, that single function is converting that histogram into this histogram. Right? So what we're going to be trying to do with this with the GANs is we're going to try and learn a function, this particular function over here. Okay, so I'm not going to be dealing with Gaussian data, but yeah. So let's go through. So let's go through the theory before we get into it. So for me, this is the thing that explains what's about to happen. So what we're going to do is we're going to generate a uniform distribution. So basically anything from anywhere on this line. And what we're going to do is we're going to have a function that squishes it into this green distribution. Okay, so the black distribution is what we're trying to get to, and the green distribution is what it's converting it into. Right, so the new distribution. And then you have the blue line. It's called a discriminator function. So what it's saying is, if you look at any data point to the left of over here, it's quite certain that it's the true data, right? And to the right of it's so from here to here, it's not quite sure because both the true data and the fake data can lie over there. But anywhere to the right of this, it's quite sure that it's fake data. Okay, so we have this concept of true data and fake data. Right? So what the generator is trying to do. Okay, so we're going to go through all this in a nice code example. But what the generator is trying to do is it's trying to fool the discriminator so that it thinks that it's coming from the true data. Okay, so we have two separate networks. One is the discriminator network, and the other one is the generator network. Okay, so as it trains, okay, so that's after the discriminator trains, what I just went through. But yeah, so in the next step, the generator will start going to the left, right? So it'll start getting closer and closer to the true distribution. And once it gets to the exact same distribution, the discriminator really can't tell what's what anymore. So it's flat. So it's actually going to give half probability of it being fake or real. Okay, so that's in a nutshell what GANs do. Okay. All right. So let me go through a concrete example. So what I'm going to have is the MNIST data set. Right. So the MNIST data set, just quickly. Let me just show you the picture. So it's a handwritten data set, right? So it looks like this. So it's a 28 by 28 image, and what we're going to do through this code is we're going to try and generate fake numbers, right? So we have the true data set, which is the actual MNIST data set, and then we're going to try and emulate what's happening over there. All right. So the generator. So the generator in this case is going to take a 64 random vector. Right? And when I say random, it's a random uniform vector, and then it's going to try and so it's going to create a neural network that's so usually you're probably used to neural networks that looks like a pyramid, right? But in this case, it's actually going the opposite way. So the first thing that I'm going to do, so the first one is the usual dense layer. So you have the 64 numbers over here. It's going to connect up into like 49 times depth. thing, and I'll tell you why I have 7 by 7 in a bit. But actually, the reason I have 7 by 7 is because I want to make it into a 7 by 7 image. Okay, and depth in this case is going to be, so depth is going to be 64. So it's going to be a 7 by 7 by 64 thing. Okay, and what I'm putting into it is Z, which happens to be not 64. Sorry, it's going to be 100-dimensional vector. Okay, so I have 100-dimensional vector which I'm connecting up onto a layer that has this many nodes, and then I reshape it just to make it like a block. And then what I have is, so this upsample operation over here, it's a transpose convolution layer. Okay, so convolutions, if you've seen them before, it's looking at a certain region and then convolving the image, but this is going the opposite way. Okay, so it's actually creating a bigger image from it. So yeah, so I have a few of those layers, and this strides thing, what it's doing is it's actually making the image wider. Okay, so every time I say strides is 2, it's multiplying the width and the height by 2. So the 7 becomes a 14, and then eventually becomes 28. So remember, I'm trying to get to a 28 by 28 image. Okay, so that's why I had 7 by 7 to begin with. So that's the generator, right? So so effectively what I've done, so forgetting about all the convolutions and everything, is I have a network that connects the 100-dimensional vector up onto this image, right? So all a neural network is a bunch of weights. Okay, forget about how you optimize it or anything. All you have is this 100-dimensional thing. You push it up onto this high-dimensional space. Okay. The discriminator, on the other hand, is something you're probably used to, right? So the discriminator, in this case, I have a 28 by 28 image, and I do the usual convolutions. Okay. I'll talk about batch normalization in a bit, but the essential idea is that I have an image that's coming in, and the task of this is to discriminate it, to say, is it a true image? Is it a false image? A fake image? Right? So that's all it has to do. Okay. Yeah. So in this case, I only have 2 convolution layers, and yeah. So that's my network, and this is the interesting part. So when we start training it, right? So when we're training it, the first thing that I do is I generate a couple of fake images given the current state of the generator. So I have inputs fake, and then so ignore the logic part. So if you take the exponential of this, you get the probability of it being real or fake, right? So over here, what I have is the cross entropy loss. Okay, so the first, for the discriminator, I'm going to give it the true labels. So for the fake data, I'm going to say it's going to be, the label is 0. Yeah, sorry, I'm jumping around, but yeah. So over here, it's a bunch of zeros and ones. Okay, so for the discriminator, I'm actually going to give it the true labels. I'm going to say, yes, this is true, this is false. But for the GAN, so this is the second loss function that I'm going to be doing. This time, so I give it the fake data, but I say that the label is true over here. I can't seem to, yeah, okay. Okay, so yeah. So I give it the fake data, but I say the labels are true. Okay, because again, the task of the GAN is to fake the data, right? So it wants to try and fool the discriminator. But one thing that I do is when I'm training the discriminator, I only change the discriminator variables. When I'm training the generator, I only change the generator variables. Right? So that's really the trick. So if I try to do this while the discriminator can change as well, it's never going to converge. Okay, so that's going to be a problem. It's actually going to clash. So what I do is I train the discriminator at one point, and then I go on to train the generator. So I go back and forth between two. Right? So it's a bit of a cat and mouse game. So I train the discriminator to say yes, it's fake and yes, it's false, and then the GAN tries its best to fool the discriminator. Right? So just to show you what it looks like. right? So, and this is a little trick that I picked up on Stack Overflow, but it's using TensorBoard if you ever played around with it, right? So you have the inputs that's come through here, and then the generator. So if I expand this out, yeah. So unfortunately, there's too much detail in there. But yeah, so you can see the convolutions, the transpose convolutions, and everything else in there. So you can expand this out and play around with it, and the code is available to play around with. So there's two discriminators over here. One's simply a copy of the other. So this is something with TensorFlow I just couldn't figure out how to get around. So all I do over here is I create a copy, but the second copy is fixed with the weights, right? So it doesn't train at all. So it simply keeps copying the things across. And I need to do that just, but if it was a proper diagram, all you would have is the z's, the random vector coming through here, through the generator, and then going to the discriminator. And then you have a second input, which is the true data that goes into the discriminator. Actually, yeah, so if I zoom in over there, the true images only go through the copied discriminator. Okay. Yeah, so let me just show you what some of the data looks like. Right? So right at the beginning, it's complete random noise, right? So that's all the things that you get. And then we start to see things starting to cluster in the middle, right? So the one, so because keep in mind this is a grayscale image, so all the values are between 0 and 1. The values start clustering in the middle, so you can see a bit of a 3, maybe a bit of a 5 if you squint. Yeah, so you start seeing 8s and stuff like that. Is it finished training? No, it's still running. But let me just show you a finished example. So yeah, so this is the kind of thing that you start seeing, right? So a better example that I did was with so there's another data set called the celebrity data set, and yeah, if it loads. Are there any questions while we wait? No? Okay. So that's the actual data set. That's not the generated ones. But if I scroll down to the bottom, yeah. So again, starts off with random, and then the faces that starts to generate are becoming more and more realistic. Right. So we're actually generating complete new data, and it's not a simple copy of what was there. Yeah. So anyway, that was the basic GAN paper, right? So there's another thing called Cycle GAN that came the year after, I think, which did things like this. So it was, to me, it was a small extension, because in the basic GAN, what you did was you took just a completely random data set, and then you converted it into an image. And one guy just came along and said, why can't I just use the existing distribution and change it to something different altogether, right? So in this case, horses into zebras, right? So it's a very simple idea, but there was a bit more than just that. So what he did was, like, you can go from horse to zebra and back to the horse again. Okay, so that's why it's called Cycle GAN. So if I show you some of the images, so that's the kind of thing that I was able to do. So summer to winter. So a lot of the applications in GAN have been, like, mainly fashion, anything to do with entertainment, right? So you can generate scenes, for example, and this thing was pretty cool. It's called Face to Face. So you took the left is the real one. So yeah, yeah. I was trying to train my face to Donald Trump, but I was still training. Takes a bit longer with him. So yeah, so that's GANs in a nutshell, right? So are there any questions about this?
I'm coming.
Thank you for the explanation. The gap I've got is you start off with converting one distribution to another,
Yeah.
and then we go from one picture to another. Could you talk a little bit about how the one relates to the other? How do you go from a distribution to change
Sure.
pictures?
Yeah. So if you look at this thing over here, so that's still a random distribution, right? So if you think about images, it's just, and especially because I have in this case, like 50,000 images off the written data set, that's effectively a distribution that we have. And so if it's sampled distribution, I think that's actually the key part of here. And actually, one thing I should mention, I forgot to mention while I was doing this, is GANs are really hard to train, right? So batch normalization thing that I mentioned before, it's one of the tricks that's used in training normal neural networks, but you really have to bring all the counts out to make sure it's stable, right? So if you look at the GAN paper, it does say there are some convergence guarantees, right? But that's obviously an ideal setting, right? So it's quite, training GANs are unstable.
I think that we are finished now.
Do you have anything more to add to your talk? Or what
No, apart from the fact that if you yeah. So, but just ask your question.
Maybe I can just let you finish, and then I will ask a question.
Okay. So the only thing that I want to mention was again, all of these things are so one of the lessons in deep school, right? So if you I did jump to one of the fairly advanced concepts, right? But it does go through all of this like very systematic way. And so I think at least it's very systematic. So it's only neural networks. I don't go into any other machine learning, method. But at the same time, I do think that there's a fairly comprehensive set of tutorials. So that's all.
Yeah, my question is actually related to the.
Thanks, Sachin.
Great.
Thank you.
Now we can officially open the floor to questions.
Sure, thank you very much for the talk. My question is actually related to the general machine learning. Do you know of any connection between the GANs and the expectation maximization, for example?
Expectation maximization.
Yeah, it's a method actually to learn the expected value of some parameters that can generate the data, or it can be applied to that.
Oh, right. But okay, so yeah, but EM was more to learn the hyperparameters, right?
Which in the Bayesian setting can be actually the distribution itself.
Right. Okay. So I don't know enough about EM to comment on that to start off with, but I should mention that when I was going through this, even though the discriminator was a neural network in this specific case, it doesn't have to be, right? You can just replace that with any other. Choose your favorite machine learning algorithm and replace it. So I'm not EM might fit in there somewhere, but I'm not entirely sure how it can.
Yep.
Is there some way to sort of measure the difficulty of mapping from one distribution to the other? And what I'm thinking of is that maybe you have a handwriting sample and you will need to know which numeric digit, for example, they're trying to write. And if you can map to this one more easily than, if you map to 2 more easily than to 6, then it would seem that 2 would be what they were writing. But is there a measure for of ease?
Not off the top of my head, but look. So one of the reasons it worked okay in this particular case was that I had a lot of data, a relatively lot of data. So that's why it worked. So if you come like one thing that it is used for is data augmentation, right? So if you're training something and you just simply don't have enough data, you can use the GAN to add more data into your data set. But again, that's if you had quite a decent data set, quite a big enough data set to begin with, right? So in terms of difficulty from training one or the other, I'm not too sure about that area.
Hi, I don't have a technical question, but more like a general question on what kind of applications do you see this having besides maybe bankrupting Photoshop or creating fake images, having more hits on YouTube? What kind of applications, professional applications by creating fake data sets do you see having?
So all the examples that I know have to do with images so far. Right? I mean, the latest thing that the face-to-face thing, or at least a version of it, did hit the news recently because they were taking celebrities' faces and then augmenting into porn stars. So yeah. So that's I don't know if the guy made any money out of that, but but yeah. Anyway, so anything to do with generating images is generally where the applications of GAN have been so far.
Great talk, Sachin. Quick question. So you mostly monitor convergence by just eyeballing the resulting images. Are there any more rigorous techniques to assess how your GANs are doing?
Rigorous techniques to
evaluate your convergence.
Evaluate the convergence.
Yeah.
I know there's been papers written on just convergence, making sure GANs can merge alone, right? So just because they're so unstable, people wrote papers on how to, all the tricks to make sure they converge. Actually, there is one way of evaluating it. So one thing I said right at the beginning was the discriminator can't tell between the fake and the real images anymore, right? So one way of measuring convergence is to see if the discriminator is starting to put half in there, right? Because once it can't tell, it gives both of them equal probability. So that's one measure. Yeah.
Thank you for the presentation. I'm actually hiding behind the table so you can see.
Yeah.
My question is regarding to your input data set. Say if your input data set, the probability of having each digit is the same, does the GAN actually preserve that distribution when generating the new data set? Or is that possible that the generator figured out that one is really easy to fool the discriminator, so I'm going to generate a lot of ones compared to other digits?
Yeah, so when I was training it, I did notice that there were some digits that it tended to do more of. So over here, they're all 9s and 8s, right? So I don't see any 3s or 7s or anything like that. So keep in mind, like it's thinking of the 9s and the 8s as one distribution rather than separate distributions as well, right? So yeah, so there's definitely a case of it might be converging towards the easiest maxima in that bigger probability distribution space, but I'm not 100% sure that that's definitely what's happening over here.
Hey, thank you so much for the interesting talk.
Yeah.
Cool. So, many of the deep nets, you have pre-trained networks that you can sort of adopt in your architecture and use them. For example, Google provides some of these pre-trained networks. Are there similar things for GANs? Can you find pre-trained GANs given that training is expensive? Does it make sense at all? Or
Yes, it does, yeah. So the pre-trained GANs in this case would have been overkill, just because. So the one case that I did use pre-train was for an image classification problem, but it was quite expensive, right? So because it already had like 16 layers. So anyway, just there were just simply too many parameters to do transposing on this example over here. In general, is there a way of using pre-trained GANs for the discriminator part? Yes, obviously, right? Because you can use the first few layers of a pre-trained image classifier, right? Just for the discriminator part. But again, keep in mind the important part of this is not the discriminator; it's the generative part. So the generative part is going the opposite way of the discriminator, right? So I wouldn't be surprised if you can use the existing things that people have used in GANs, because end of the day it's just a neural network, right? So you can still use the first few layers. I don't see why you shouldn't be able to not use it. So the last few layers is what's going to be domain specific. If it's endless, it's going to be endless specific layers. But yeah, so the first few layers should be the same. Yeah.
Thanks for the talk. Thank you for the talk. It was really interesting. So, just out of curiosity, the distribution that's been generated, which is the fake distribution.
Yep.
In the example of the
celebrity images. So would the outputs be effectively the reconstruction of similar images, or would we see like a human being were to scan the images? Would those be very different? But only the algorithms now, or the discriminator function is not being able to tell the difference. But for a human being, would be able to say that, okay, so it's not the image of the same people over and over again, it's something new that has come out of the model.
So the specific example that I did, you can clearly tell that's a fake image, right? So if I go to the actual data set, it's quite crisp, I think. Oh, not crisp, but at least you can see it's actually human faces, right? So that's a real data set, and the generated ones are the best ones that I could generate. I mean, they're getting there, but yeah, so that's fairly all right. But there was a recent paper that did high definition GANs, right? So it was successfully, like it was really good in generating. It was still from celebrity data set, but yeah, it generated high resolution pictures. So I'm not sure how that worked or how they did it, but yeah, you can definitely do that. So and the other thing is keep in mind, one way of thinking about this problem is that you're taking effectively you're transforming a small dimension into a large dimension set. So effectively that's what you're doing. So yeah.
So just wondering, are there much example of using the GAN for audio data, like maybe for like a noise cancelling, or maybe for image for like a cloaking mechanism, like a tank or something?
Right. So in terms of noise generation, so I don't know if you mentioned Angela. So she did a talk a few months ago, and so from the little bit that I remember, in terms of generating noises, what you have to do is first of all convert the noise into a FFT image, and from that you generate the FFT images and then convert it back into noise. Right, so the fast Fourier transform, or something along those lines. So can you get rid of noise from that? I think there are other machine learning techniques to get rid of noise itself. The only way that you can get rid of noise is if you had a data set that didn't have noise to begin with. So from that you can learn the distribution of normal voices, right, and get rid of distributions that are noise effectively from that. So that's the only way I can think of using it.
Quick question over here. I'm wondering, you're dealing mainly with images and classification of images.
Yeah.
I was inspired by one of your lessons there. It said fake news or something like that.
Sure.
Would it be possible to? I'm thinking of news sentiment. So
yeah.
Financial trading companies might use news sentiment counts as a data stream. Would it be beneficial in any way to try and create fake news articles and see how your discriminator is with that?
Yeah. So in terms of generating news articles, that's actually I don't know if you have time, but so that's a Shakespeare generator, right? So it read through all the Shakespeare texts and generated Shakespeare. I actually went on to do a Trump tweets generator as well, but that had nothing to do with GANs, right? So that was pure recursive neural nets. It didn't have a discriminator component to it at all, right? Would it do better with the discriminator? Yeah, probably, because you have this trainer that says, no, I'm going to penalize you if you got the wrong thing.
Two more questions, one here, one there.
Hey. Sorry, I just had a quick question. One of the things we spend a lot of time on doing is imputation of missing data for our training sets.
Yep.
Is this? I mean, have you seen this method used effectively in comparison to other imputation methods?
So I haven't used this in practice, right? I've only done this as this is a very academic problem because it's got a nice data set over here. But yeah, so that's the idea of using GANs in the first place, that you can augment your data set. That's one of the goals, right? Because what you're trying to do is you're trying to generate your data distribution, which you only had a sample of to begin with. Does that answer your question?
I was just wondering whether you've seen it used, like how effective it has been.
Yeah, again, I haven't used it in practice, so I'm not too sure.
One last one here.
Yes, so my question is that, is there any criteria or selection criteria to select the layers and the neurons, number of neurons in a generator and the discriminator?
Right, okay, so
there's another one. So basically, so for like comparison and the convergence, like this question has already been asked, I want to make it more specific. So in order to compare the two distributions, they converge to each other. So are you using any criteria like KL divergence or versus time distance, something like this?
Right, okay. So with the KL divergence part of the question, I think you need to have you need to have parametric version of the distribution, right, to compare the two. I suppose. Okay, actually. Yeah. Anyway, we'll talk about that later. But like for now, at least, I don't think you can use KL divergence as it is to compare the distributions and go, yes, this converge. So for now, all I'm saying is the probability, the discriminant probability does it converge to half. So that's what I could think of. Now coming back to the number of layers, number of neurons. One thing that I do in this thing is I do make the discriminator a bit weaker than the generator, right? So I make the generator a bit more powerful. That's just one of the tricks that you learn when you just do read blogs and stuff. Just because the generator is really what we're going to focus on, not the discriminator. The actual number itself is very much trial and error, as it always is with neural networks.
Thank you very much. A fascinating discussion. Please join me in thanking Sachin. And I'm sure you'll be around for questions after the next talk as well.